The first several thermo videos deal with defining some key terms and conceptually what's happening to the particles as we heat up, cool down, increase and decrease in temperature. Calorimetry is where we take that idea of heat transfer and energy and measure that in the lab. As we are measuring things in the lab, we are looking for changes in temperature that we can directly tie to the gain or loss of heat as when defining something as endo or exothermic. The transfer of heat is related to the first law of thermodynamics, or sometimes it is stated as the law of conservation of energy. It says the total energy of the universe is constant, or when we're applying it, we're really thinking about this energy lost by a system is gained by the surroundings and vice versa. We aren't creating energy, nor are we destroying that. So when I have something that's hot and something that's cold, if I know how much heat is transferred, I can make connections to the temperature change, or if I know the temperature change, I can make connections to the amount of heat gained or lost. As we do that, we need to make the connection between heat and temperature. We have an equation here that maybe you're familiar with. We've got all our variables with their units defined, and we know that heat and temperature are not exactly the same, but the connection between them is the idea of the energy needed to make our particles on average move faster. We need a variable for how many particles we have, which is the mass, and then a variable for basically how hard is it to get those particles to move faster. And that would be defined as the specific heat. The equation Q equals mc delta T is given, and it's very useful whenever we're thinking about a change in temperature. So when you see an object heat up, cool down, a final temperature, this is what you're going to be looking at, and you're going to be making connections with mass to calculate the heat, which will be in joules. The units, and we'll see this later, but the more we hear it, the better. The units are super important here, that we pay attention to those, that we make sure that they cancel, and we make sure that we understand those. Calorimetry experiments are any experiments where we're thinking about measurements of mass and measurements of temperature change to think about the heat flow. Sometimes we are solving for a specific heat. Sometimes we are solving for a heat lost or a heat gained. And when we're doing that, we want to minimize heat lost to the outside surroundings. So we often do it in a calorimeter. That's just an insulated container that has a way to measure the temperature, a thermometer that can go into that, and often something to stir it or to help that transfer of heat go a little bit faster. With the first law of thermodynamics, we know that the heat lost and heat gained are equal in magnitude, but they're opposite in sign. One thing is gaining and one thing is losing. Units are important in thermodynamics, but the sign is also important. Because if one thing's going up in temperature, it would have a positive delta T. The other thing, therefore, would be going down in temperature and would have a negative delta T. As I try to connect that heat lost and heat gain to one another with the opposite signs on T, we recognize that this negative sign is there just to remind us that they are opposite in direction of flow as well. That positive or negative sign doesn't really mean we're on opposite ends of a number line so much as we are thinking about the opposite direction of flow, or we're thinking about gaining versus losing it. One easy way, or one direct way that we will see for knowing the heat, is just mc delta T. But we're going to make connections in terms of heats of reaction, which have other variables. We're going to make connections with changes of state, which have other variables as well. So however we're doing this, the total heat gained and the total heat lost are opposite in sign. It doesn't matter which side you put your negative sign on, but they are equal. And if we just have objects transferring heat back and forth, which is what many simple calorimetry experiments do, maybe a hot piece of metal in cold water or hot water in a cold piece of metal, it's just the mc delta T is equal to the mc delta T accounting for signs. There are other variables that are really closely tied to this. One thing that is sometimes used for an experiment is a bomb calorimeter. In a bomb calorimeter, and I'm kind of jumping down here, in this case, we don't think about the mass of the chemical reacting because the calorimeter itself has a has a heat capacity. So we'll see we have specific heat, which we've already talked about, heat capacity, which is slightly different, and molar heat capacity. All of these are variations on the same thing. How does the temperature change relate to the heat? Heat capacity is the variable that makes the direct connection there, a measure of a system's ability to absorb thermal energy as it's changing its temperature. The heat capacity accounts for how many particles you have and how easy it is for those particles to increase in kinetic energy. It's often related to the state. It's often related to the strength of the attractions between the particles, whether they're IMFs, intermolecular forces, or bonds. But if we have a larger or smaller sample, if we have a solid versus a liquid, the heat capacity changes. That's why the specific heat or specific heat capacity is often more valuable. It includes a factor for mass so that we can know per gram how much heat is needed to change the temperature. That's what you're going to be doing most of your calculations with. And the units on heat capacity and the units on specific heat help us to know which one we are given. We could also be given heat capacity in TET instead of for the whole object, or instead of per gram, we could be given per mole. It's the same definition, how much heat is needed to change the temperature, but now it's per mole. So with all of those, we don't need to or even want to define a whole bunch of different equations. We just want to see, well, what is the variable we are given that connects heat to delta T? It can happen in different types of calorimeters. It can happen in different scenarios. We can be given different information based upon that, but it's all centered around that transfer of heat in connection to maybe just a temperature change, sometimes a phase change, or sometimes a chemical reaction. But in all those cases, we want to make careful measurements. We want to minimize heat lost to the surroundings while acknowledging that is a very possible source of error. And we want to recognize what we do measure and what we don't measure. We often measure the mass of our reactant, of our system, of our amount of water. We measure the initial temperature and the final temperature of maybe our surroundings, of the water, of the air, of the calorimeter. But the heat itself and the specific heat are calculated values or given values. So when we're thinking about our experiment and our experimental error, those are important factors to consider in addition to the units and the sign